Good day, everyone. Welcome to lecture number 7 of Theory of Computation. And in this particular lecture, we will start discussion about the finite automata. But before discussing the finite automata, let me recap what we have discussed in our last lecture. The first thing that we discussed is the automaton. What is an automaton? Okay. So as we know that automaton is a mathematical model of computation. Okay. Model of computation. Fine. The second thing that we discussed was a problem. What are the problems? Or basically we discussed about the language, but let me skip that portion here. So the second thing was a problem. So what was a problem that we will be going to discuss using our mathematical, or we will going to address in our mathematical model of computation was that if we have a string, have a string, can we say whether it belongs to some language? Some language, some formal language. Okay. So this is the problem that we are going to discuss in our, we can say, the entire course, or we can say we will discuss these mathematical models such that they will be able to answer this question. So since we have different language, so that means we need a different automaton, or we can say different mathematical model for every language. Fine. So our discussion will be related to the first related to the automaton, and also we will discuss how we can use these automatas to address this problem. Fine. And in today's topic, our first job is to discuss the first class of automaton, that is finite automata. Okay. We have to discuss about the finite automata. So what is a finite automata? A finite automata is a simple mathematical model, and this mathematical model will help us to understand whether a string S belongs to a language L. Okay, so this is a simple automaton that will help us to determine whether a string belongs to a language L. However, this particular automaton won't be able to answer this question for all the languages. It will be able to answer the question, this particular question, for only some of the languages. Okay, so finite automata is a mathematical model. As I said, it is a simple mathematical model, and it will help us to determine whether some string S belongs to a language L. Okay, but I am saying that this machine, this mathematical model won't be able to solve this question, or we can say it won't be able to tell us whether a string S belongs to a language for all the languages. It won't be able to answer us for all the languages. It will be able to answer us only for one class of languages. One class of language. Okay, but there are some other languages or this class of language for which our finite automata will be able to answer. These languages are called regular languages. Fine. So what is a regular language? We can say here a regular language is a language. It is a language L such that we have a finite automata that can answer the following question for that language. The following question for that language. And what is the question? The question is whether S is a string, whether S belongs to L. Okay. So regular languages are those languages are those languages for which we have a finite automata. What is a finite automata? We will discuss this in detail. What is a finite automata and how to build a finite automata. But here I am saying a regular language is a language such that we have a finite automata that can answer the following question for that language. And the question is whether a string S, any string, belongs to a language. So if we have a finite automata M, let's say this is a finite automata. Okay. And I have a language L, let's say M1 and L1. And this M1, this finite automata M1 is able to answer whether a string S belongs to L. If this automata, this finite automata is able to answer this particular question for all possible strings, then we will say that this automata, this M1 accepts L1, or we say M1 recognizes L1. Okay, and also we say that L1 is a regular language. So what is a regular language? A regular language is a language such that there exists a finite automata for that language. Existing a finite automata means that that particular automata will be able to answer this particular question, and it will be able to answer this question for all possible strings. So we say that language of this automata M1 is L1 if it is able to answer this question for this particular language. And we also say that M1 accepts L1, or we say M1 recognizes L1. Okay. So now what is a finite automata? So here I am saying about, I am discussing, or I am using the term finite automata repeatedly again and again, but we have to understand what is a finite automata. Okay. So before making you understand a finite automata, let me give you an example. Let's rub these things here. Let me rub these things and I will give you an example. And after that example, we will discuss what is a finite automata. So let's take an example of a toll gate. So what is a toll gate? For example, you may have seen in your daily life a toll gate. So toll gate is the gate that is used at the parkings. Mostly it is used at the parkings. And the functionality of the toll gate is that if you put money, it will open. Okay. However, if you are not putting money in the toll gate, it won't open. Fine. So let's say we have a toll gate. Okay. It accepts currencies. So what it accepts? Let's say it accepts 5 rupee note and 10 rupee note. Let's say 5 and 10. And toll gate opens if our total amount is, let's say, 20. If the amount is 20, then it opens. However, if the amount is less than 20, it won't open. If you put money 20 or greater than 20, it opens. However, if you put money less than 20, it won't open. So let's see the state of this toll gate, or we can say, let's make a model of this toll gate. Okay. The model of the toll gate is, we have an initial state of the toll gate. Initial means initially the initial condition of the toll gate. Okay. Then let's say someone comes and he wants to enter into the parking. So this toll gate should open. So he will put money. So what are the possible currencies that he will put? Let's say he put first 5. Okay. Will gate open? No. Then again he will put 5. Will gate open? Yes. Then again he will put 5. Will gate open? Sorry, 5. 5. Will gate open? No. And then again he will put 5. Then gate opens after putting 5, 5, 5, 5. So if you see, we have the state of the toll gate. We have the initial state. Initial state means no money has been put into the toll gate. Then some other state, let's suppose state 2. State 2 means that 5 rupees have been put. Let's suppose state 3 means total 10 rupees have been put. State 4 means 15 rupees have been put. State 5 means 20 rupees have been put. 20 or more than 20. Now let's make a diagram, or we can say the state diagram of this toll gate. So let's say this is one state of this toll gate. So this is the initial state. Let's represent it by S0. So let's say this is initial state and it is S0. Okay. So this is the start state. In the start state, if I put 5 rupees, then my state of the toll gate will change from 5 to which state? S2 state. It will go to S2 state. However, if I put 10 rupees, so there are only two currencies, 5 and 10. If I put 10 rupees, where will it go from S0? It will go to another state, that is S3. So basically this state diagram, it will be like in toll gate, we will have, let's say, it will be a small computer. In the small computer, let's say we have a memory, and this memory is storing the current state. Initially the state will be S0. If I put 5 rupees, then this memory will get updated with S2. Okay, but here we are showing the complete model. How will the states change upon these currencies? Okay, so if I put 10, it will go to S3. Now if we are in S2, in this state, if in the memory we have stored S2, if will this gate open on S2 if it is in state S2? So it will check its memory. The memory is saying that it is in state S2. Will it open? No. S2 means that only 5 rupees have been put into the toll gate. If it is in S3, will it open? No. again it won't open. Why? Because it means that only 10 rupees have been put. Now let's say we are in S2, and let's say in S2 user has again put 5 more rupees. Which state it will be in? S2 means that 5 rupees have been put, and again another 5 rupees means 10 rupees, which is the 10 rupees state S3. So that means it will go to S3. Fine. However, if it is in S2 and the user has put 10 rupees, then it will go to which state? The state storing the information about 15 rupees. That means the S4 state. So if it has put 10 rupees, then its state will be S4. Okay. Now let's say we have reached to S3 state. What are the possible ways of reaching the S3 state? One is initially the driver of the car who wants to park into that parking. So initially, let's say he put 10 rupees, then we may have reached S3. The other possibility is he may have put first 5 rupees, then 5 rupees, we have reached S3. Now let's say we are in S3. S3 means we have put how many rupees? 10 rupees. So from S3, if the user put 5 more rupees, so S3 means 10 has been put. 5 more means that it will go to this state, S4 state, because it is a 15. However, if user put 10 more, 10 more means it will go to S5 state. S5 means more than 20 or more than 20. Okay. Is there any possible state from S3 apart from these two? No. Now let's say if it is in S4, S4 means 15. So if the user put 5 rupees, it will go to S5 because 15 plus 5 is 20. And if user put 10 rupees, 10 rupees again means more than 20. So on both 5 and 10, it will go to S5. Now on S5, if it is in S5, S5 means if the state of toll gate is S5, then that means it has to open the gate. And after opening the gate, if it closes again, the memory becomes again S0. S0 means the next driver has to start from this particular state. Okay, so this is a diagram that represents toll gate mathematically. Okay, or we can say, because toll gate is a kind of computation model. Okay, so this mathematical model represents this toll gate. So this is an automaton for toll gate, because automaton is a mathematical model of a computing machine. So it is a mathematical model of a toll gate. So you can see here that this particular state, S0 state, this is a spatial state. Spatial state means that this has spatial meaning. Spatial meaning means always we start from this state. Always start from this state. Or it is also called an initial state. Okay. And this S5 state is also a spatial state. Why it is a spatial state? It is a spatial state because when we reach to this state, it means that gate should open. Okay. However, if my state, the state of my automata is any other state apart from this state, let's say S0, S2, S4, or S3, will my gate open? No, the gate won't open. So these states, so my gate will open only if I am in S5 state. So this state is also called a final state, or we also call it accepting state. Okay, and these states, for example, S0, S4, S4, S3, these are called non-final states, or we also called non-accepting states. Okay. So this mathematical model of a computer, sorry, of any computing device, this type of model is called an automata. So you have seen this is an automata. Okay, this is an automata. And what are the features of this automata? What are the different components of this mathematical model? The first component is we have states. Okay, or we can say we have set of states. So how many states are here? So let me rub some portion to make some space. So what are the possible features of this automata? So this automata has some features. First is we have states, or we also called state set of states. Okay, so what are the set of states here? One is S0, this is one state. S2 is another state. S3 is another state. S4 is another state, and S5 is another state. Okay, so this is represented using Q. Q, that means we have set of states. Second thing, what we have, what are the second thing that we have? We have one spatial state that is called an initial state. So initial state, the states in automata, they are usually represented using like this: Q0, Q1, Q2. Here I have written S0, S2, S3, S4. This will also, you can represent it like this, or you can use Q0, Q1, Q2, Q3, and so on. So we have an initial state. In this diagram, we have S0 as initial state, or we can say the initial state is denoted by Q0. And third, we have another spatial state. That spatial state is the final state. Okay, so in this particular example, our final state is S5. You can see how will you recognize the initial state in the automata? You will recognize the initial state in the automata when we have this arrow and there is nothing written on this arrow. So on all other arrows, there is written some symbol. So here the symbol is 5, here the symbol is 5, here symbol is 10. But in the initial states, this particular arrow, there is nothing written on this. So in some of the diagrams, there is directly written start. Start means that it is the initial state. So initial state, we can recognize the initial state by this particular arrow. Okay, how will we recognize this final state? So how will we differentiate final state from non-final states? So the final state is differentiated from non-final states by making two circles. So in this diagram, so this diagram is called a state diagram. So in the state diagram of an automata, if we have a state with two circles, that means that particular state is a finite state. So that particular state is a final state. So the final states are enclosed in double circles. Okay, so here our final state is S5. The fourth thing that we require is that the symbol is set. Symbol is set. So what is a symbol set here? So here we are making these transitions. So we are making a shift from one state to another state by these symbols. So what are the symbols here? The symbols are these two. So what is the symbol set? It is also called an alphabet set. Okay, and it is denoted by sigma. So our alphabet set is 5 and 10 in the toll gate example. And the last thing, the fifth thing that is there, can anyone guess what is the fifth thing? The fifth thing is transition function. What is a transition function? So the transition function is saying that if, let's suppose I am in state 0. Now in state 0, if the input is 5, I will go to state 2. However, if the state is, let's suppose state is S0 and the input is 10, or we can say the symbol is 10, we will go through S3. Okay, fine. That is given with the help of a transition function. I will explain this transition function in great detail, but let's wait for a few minutes. So let me summarize this portion up to this. So I said then automaton is a mathematical model for any computing device, and we have shown one mathematical model for a toll gate. Now let me show another mathematical model, then we will discuss these 5 things in detail. Okay. So let me rub this portion here. So let me make a simple automaton here. So let me make this. So this is a automata, okay, a simple automaton. Let's see what is this doing. So this is saying that we have to start from this particular state. So in this automata, we have 2 states. So we can say our Q is this Q0, Q1. Okay, this is our states in this automata. So what is this automata is doing? So let's take this automaton, okay, this particular automaton. We said what is an automaton? We already said an automaton is a mathematical model of a computing device. And what is the problem this automaton is going to solve? This automaton is going to solve the following problem. The problem is, if we are giving a string, it will tell us, whether it belongs to a language. This thing you have to keep in mind, and when we discuss this example, I will show you how this automata is answering this particular question. Now let's come here. This again, this automata. So let's give this automata a string. So this is a string. Okay, so this is a string of zeros and ones. So what is the alphabet set for this string? Alphabet set for this string is 0 and 1. Okay, fine. So you can determine this alphabets from here also in the diagram itself. So what are the symbols here? 0 and 1. So the alphabet set for this transition diagram is 0 and 1. Okay. Now let's say we are giving this string to this automata. So it will start from this. So first symbol is 0. 0 means it will go to Q1. So let me write it here. So first it is Q0, so it is getting 0. So then it will go to Q1. Fine. So on accepting Q0, on accepting 0, it will go to Q1. So that means it has processed this particular symbol. Now current state is Q1. Now Q1 is accepting which? 1. So Q1 on seeing 1, where will it go? It will go to Q0. So the current state is Q0. So 1 is completed. Now on Q0, it is seeing which symbol? 0. So Q0 on 0, it will go Q1. 0, it will go Q1. So this is also completed. Now we have this particular Q1, the input is 0. Now on Q1 on 0 will remain there on Q1. So because it is saying Q1 on 0 will come again here. Now we are on Q1. Our current state is Q1. Q1 and the symbol is 1. Symbol is 1. So Q1 1, we are going to Q0. So is there any other symbol in the string? No. So we have completed processing of this string. So after completing this string, processing this string, what is the state? In which state we are? We are in state Q0. Okay, this particular state. Fine. So after processing this particular string, we have reached which state? Q0 state. Is Q0 state final state or non-final state? It is a non-final state. Okay, so in our automata, when we are giving the string to an automata, after processing entire string, it will at the end reach to some state. So after processing the data, it will reach to some state at the end state. If the state is non-final, so there are only two possibilities. One is that state is non-final and another is that state is final. Okay, if the state is non-final, so here the state is non-final, then we say this particular automata does not accept, let's name this string as S1, does not accept L1, or we say it does not recognize S1. Okay. And if the automata after consuming this string reaches the final state, we say it accepts S1, or we say it recognizes S1. Fine. So our automata, we can say this particular automata, when it receives a string as input, it will process that string symbol by symbol. It will process the string symbol by symbol. And after processing the entire string, if it reaches to a non-final state, we say that if it reaches to a non-final state, we will say that it answers no. Answers no means that it does not accept this particular string, or we can say it does not recognize this string. However, if after consuming this string, it reaches to a state and that state is final, we will say that it answers yes. Answers yes means that it has accepted this S1, or we can say it has recognized this S1. So in this automata, we can say our states are Q0 and Q1, alphabet is 0 and 1. Is there any other symbol? No. And our this, what we say, the initial state is Q0, initial state. Okay, then after the initial state, our final state is represented by S. Basically, in an automata, there can be one or more than one final states. Okay, so what I am saying, there can be only one initial state, but there can be multiple final states. So here in this example, we have only one final state, but we will see some of the examples where we have multiple final states. So F is a set, that is the set of final states. So what is the final state here? In the set, there will be only one, that is Q1. Q, this symbol state, initial state, final state. Then the last thing is what we require. So this is the formal definition of an automaton. So you can represent automata using three different methods. One is making a state diagram. Okay, one way of showing a automata to the users is to make a what I say state diagram. The other way is to define it formally. So here I am defining it formally. So when you are defining an automaton formally, you have to tell what are its states, what is the symbol set, what is an initial state, what are the final states, and also one thing is missing. What is the thing that is missing in this? These transitions. So how we transition from one place to another place, or we can say one state to another state. Okay, and for that we have a transition function. Transition function. So what is a transition function? So here it is saying if I am in Q0 and I will see 0, I will go to Q1. If I am in Q0 and I will see 1, I will go to Q0. Okay, if I am in Q1 and I will see 0, I will go to Q1. And the last one is if I am in Q1 and I will see 1, I will go to Q0. Okay. So this particular thing, this transition, it is represented with the help of a transition function like this. So we represent this like this. So this is delta Q0 comma 0 is equal to Q1. Okay, and likewise for this one we can write delta Q0 comma 1 is equal to Q1. Like way you can write for this one and this one. So this is a transition function. Okay, and what is the input to this transition function? The input is current state. We can say the state and symbol, and the output is the state. So we can say delta, which is a transition function. It is a transition function from this to this. What does this mean? It means that it has two inputs. One will be a state from this set, okay, any state from this set, and another input will be any symbol from this alphabet. So you can see that one input can be state, any state from the state set, and another input is any symbol from the alphabet set, and output is any state. So output can be any state. That means, so let me rub the things here to make the things clear. So it means I need 5 things. 5 things about automata. And what are those 5 things? The first thing, I will require the set of states. Okay, the set of states will be Q. Second thing that I will require is the initial state. That is Q0. Third thing that I require is the alphabet set, or we can say the alphabets, that is sigma. The fourth thing that I require is the transition function. Okay, transition function we denote by small delta. And the fifth thing is I need final states. So these are the 5 things that I should know about the automata. Okay, so these are the 5 things that we should know about the automata. Set of states, initial state, alphabets, transition function, and final state. Either we should have this diagram or we should have this formal definition. So this is called state diagram, and this is the formal definition of an automata. Fine. Now, what is a finite automata? So basically, we have to discuss about the finite automata. So what is a finite automata? Finite automata is same that it is an automata. Automata means that it has following things. What things it has? It has the states, it has the initial state, it has alphabets, it has transition function, and it has finite state. But it has some additional features. What? The first thing is number of states is finite. Okay. The second thing for a finite automata is every state can remember only finite information. So what is a finite automata? A finite automata is an automaton which has states, which has an initial state. It works for the set of alphabets. It has a transition function. It has final states, but the number of states are finite. Number of states are finite, and every state can remember only finite information. So let me rub these things and let me make you understand finite automata. So let me write the finite automata in, we can say formally, a finite automata we know is a mathematical model M, such that M is a 5-tuple entity. Okay, that is M is equal to Q, fine, sigma delta q0 f, where q is equal to q0 q1 dash 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 is the set of states, alpha bit is set of symbols, okay, delta is a transition function, okay, transition function from set of states and input symbols to the states. It is also called a transition function. Okay, and q0 is the initial state, and f is the set of final states. Fine. And this finite automata has some features. First is number of states is finite. And the second is each state can remember only finite information. Fine. And this finite automata, if I give a string to this finite automata as input, string is input, it will answer me yes or no. Okay, it will answer me yes or no. And yes, if it answers yes, it means that after completing processing this string, it has reached to a state, and that state belongs to, so it has reached to a state and that state belongs to this particular set, final state set. Okay, and it answers no if it reaches to a state q dash such that it q dash does not belong to f. So we say this particular automata m accepts a string s if after consuming, or we can say after processing, after consuming s, it reached to one of the final states. Okay, now let's make this final this sorry we can say using this particular definition, let's write this particular automata we can say in informal way. So this particular automata, you can see that this is a finite automata. Why it is a finite automata? Because here we have only two states and these states are finite, so that is why it is a finite automata. So first thing that we have to see, what is q here? So q is q0 and q1, or we can write, let me rub it. So this is automata m. Let's say m is equal to q q0 and okay. Here what is q? Q is Q0 and Q1. What is this sigma, or we can say alphabet? Alphabet is 0 and 1. And what is delta? Okay, so delta, as I said, it can be represented in two different forms. The first form is I will write the definition of delta for every state and every symbol. So let's first take state Q0. So delta Q0, 0, what will be the answer? And delta Q0, 1. Will there be any other possibility for Q0? So if I am in state Q0, I can see only two symbols, either 0 or 1. Likewise, if I am in state Q1, so what are the possible scenarios? It can be either 0 or it can see either 1. Fine. And I have to see the output. So on Q0, if it is seeing 0, what will be the next state? Q1. If it is seeing 1, so if it is seeing 1, it is remaining there. So if I am in Q1 in this state, and if I see 0, 0 means go to this state, back to this state. And now if I am in Q1 and I am seeing 1, 1 means go to Q0. So this is the transition function for this particular, we can say, automata. This is one way. Okay, I will make you understand another way, but let's first finish this. And what is Q0 here? Q0 is initial state. So let me rub it. So Q0 is our Q0. And what is F? F here is Q1. So this is the formal representation of this particular finite automata. Fine. So as I said that I will show you another way of representing a transition function. So another way of representing a transition function is to represent it with the help of a table. So we will make a table. So how to make a table? So go like this. Okay. So here we write symbols. So what are the possible symbols here? Only two, 0 and 1. Okay. And here we write states. So in the first row, we write symbols, and in the first column, we write the states. So what are the states? Q0 and Q1. Okay. Then we will see if we have Q0 and on Q0, it is seeing 0, symbol 0. What will be the output? The output will be Q1. So that means the output will be Q1. So here we are writing that if I am in this state and I will see this particular symbol, 0 symbol, okay, what will be the output? The output will be Q1. Likewise, if I am in Q0 and I will see 1, what will be the output? Q0. If I am in Q1 and I will see 0, I will remain in Q1. And if I am in Q1 and I will see 1, symbol 1, I will go to Q0. So you can represent transition, these transitions, these arrows, transitions, either using this kind of thing. This is called using a transition function. So either you can write a transition function or you can write a transition table. This is called a transition. Only you have to remember that when you are making a transition table, the final states, we put this star before final states. Okay, so this star means that this is a final state. Q1 is a final state. Here it is a final state. Okay, so this is how we make a transition table. Now let me remove this transition table from here. Let's only function on using transition functions because it is very simple. So let me rub this thing here. So this is my automata. Okay, finite automata. Now let's do thing. Let's give this string as input to this particular finite automata. So let's see how we can process this particular string. So let's say we don't have this diagram. We have only this particular thing, this formal definition. Okay, let's say we have these things. Then let's say how will we process this particular string. So it is 0 1 1 1. Let's see. Let's not look at the diagram. Let's use this formal definition. So what is the initial state? Initial state is q0. So that means initially we are in q0. So we can say our current state is q0. Now we have this input. So first symbol is 0. Okay, so we have to process 0 first. Fine. So our state is q0. And which symbol it is seeing? It is seeing the symbol 0. So we have to see what is the output. So how will we determine the output? We will determine it with the help of a transition function. We will see that transition function says when we have state q0 and symbol is 0, we will give to q1. So if we have symbol q0 and it is 0, we will reach to q1. So after processing 0, our current state will become q1. So this will be our current state. Now we are in q1 and we are seeing this particular symbol, one symbol. So delta q1, and what is the symbol? The symbol is 1. What will be the output? The output we have to go here. So it is this one, this particular one. Okay, so we will reach q0. So that means our state will change from q1 to q0. Our current state will become q0. Now we are in q0. Now we have to process 1. So delta q0 comma 1, where we will reach q0. So using this particular transition. So what will be the current state? The current state will become q0. Is there any other thing here? No. What is the last state? q0. So is this state final? So let's see if it is final. So which one is the final? Final is q1. So that means this particular automata, this automata, okay, it does not, so or we can say it will give us an answer no. So it will give an answer no. What does that mean? No means that it has reached to a state that is non-final. Okay, after reaching to a non-final state, that means it has not accepted this string. Let's say this string is s1. It has not accepted s1, or we can say it has not recognized s1. Now if I give any other symbol, so sorry, if I give any other string, so this was s1, let's take any other string of your choice. So you can use any string, let's say 0 1 0. Okay, after processing this string, this particular string, so if you process this string, you try out. So let's try out from the diagram. So first is 0. From q0 to 0, it will go q1. Now we have 1 to 1, it will go to q0. Now again we have 0. 0 means q1. So what will be the last state? The last state will be q1. And we know q1 is a final state. It is a final state, but this was not a final state. Okay, so since it is a final state, so our finite automata will answer yes. Yes means that it has accepted this string, let's say this string is s2, it has accepted s2, or we can say it has recognized s2. Okay, so how will we say it using this particular transition function is, so first we said that initially q0 it was seeing 0, it reached to q1, then from q1 it saw which symbol 1, it went to q0, then on q0 it has seen symbol 0, so it reached to q1. So this is how you represent it using a transition diagram. Sorry, using a transition function. Fine. So in a state, so here I am writing it. So let me rub it first. So let me end this particular video here, or we can say this particular lecture, and we will continue the discussion from this particular point in our next lecture, that is lecture number 8. And in that particular lecture, we will discuss, so first we will summarize the things that we have discussed here. And apart from that, we will also discuss extended transition function. Okay, and we will also have a discussion on the language of an automata, of a finite automata. And the third thing that we will discuss in that particular lecture is designing a finite automata, or we can say designing an automata. Let me stop this particular video here. Let's meet in the next lecture where we are going to discuss these specific topics. So let's meet in the lecture number 8. Till then, goodbye.